equilibrium constant and expression. Okay, there is a mathematical relationship between the concentration of the reactants and the products that's independent of the initial concentrations of the chemicals. So for any general reaction, this is a straight up little a. The lowercase letters are the coefficients, and the capital letters are the compound, molecule, element, whatever it may be. Okay? So an equilibrium expression looks like this. Here we go. K constant, so K, it's just a constant. It's a number that you're going to create. Is related to the product to the power of the coefficient multiplied by the other product to the power of its coefficient divided by the reactants to the power of their coefficients. Okay? When we go, we probably haven't seen this for a while. Rectangular brackets means concentration. The last time we would have seen this would have been like when we did pHs and concentrations. So the mathematical relationship exists for all equilibrium systems and produces an equilibrium constant or a K constant. Okay? In a chemical system at equilibrium, the constant ratio between the concentration of the products and the concentration of the reactants. So the law of chemical equilibrium. In a chemical system at equilibrium, there is a constant ratio between the concentration of products and the concentration of reactants. It is not dependent on initial concentrations. The equilibrium constant has no units, right? If I divide moles per liter by moles per liter, I'm going to end up with a 1. Let's look at an example. So here's lovely old hydrogen reacting with iodine to give us hydrogen iodide. It says write out the equilibrium expression. Equilibrium expression is this. Kc is equal to the products. So Hi, it has a coefficient of 2. So we're going to square it. Divided by the reactants, H2 and I2. That's the equilibrium expression.
Well, wouldn't you square the H and I?
Why? There's no coefficient out front of them. It's a good question to ask. H2 is not the same as 2 H2s or 2 H's. The coefficient out front of hydrogen is 1. The coefficient out front of iodine is 1. Okay? It says at equilibrium, this is your key word here. Doesn't matter what the initial concentration is. At equilibrium. That's critical. The concentration of hydrogen gas and iodine gas was 0.022 moles per liter, and the concentration of hydrogen iodide gas was 0.156 moles per liter. Calculate the equilibrium constant. So we're going to take this formula that we just created, and we're going to simply plunk in the equilibrium concentrations. Not the initial, not the final, the equilibrium concentrations. And we get what for a value? Okay, so 50.28. When we go back to significant digits, our answer is actually what? 50 point what? 3. 3 significant digits. Okay, there's no units on equilibrium constant because mole per liter divided by, if we did a unit analysis, moles per liter squared divided by moles per liter times moles per liter gives us what? We're going to have moles squared per liter squared divided by moles squared per liter squared. So there is no units. Okay. Consider the following equilibrium system at 487 degrees Celsius. 2 SO2s plus O2 gives us 2 SO3s with a K constant value of 35. If the equilibrium concentrations of the SO2 and O2 are 0.15 and 0.18 respectively, what is the concentration of SO3? So here, equilibrium concentrations. That's key. We know that Kc is equal to the products raised to their coefficients divided by the reactants raised to each of their own coefficients. So SO3 is a product, and its coefficient is, and then SO2 is a reactant, and its coefficient is, and then O2 is also a reactant. Okay? So we would have 35 is equal to SO3 squared divided by 0.15 squared multiplied by 0.18. And I am looking to solve for this. So I'm going to go 35 multiplied by 0.15 squared multiplied by 0.18. I'm going to square root it all, and I'm going to get the concentration of SO3. And that value is going to be what? Okay, so it's the concentration raised to the power of the coefficient. All right, there's a little sentence up here that you don't have. I'm going to write it off on the side, so give me a second. So you have to add that line in. The equilibrium constant, Kc, is a ratio that relates the concentration of products, that's what's missing in your notes, to the reactants at equilibrium. So the concentration of both aqueous solutions and gases can change during a chemical reaction. So it always needs to be included in an equilibrium expression. Okay? So gases and aqueous solutions. In a chemical reaction, the amounts of solids or pure liquids will change, but the concentrations will not. So let's look at the equilibrium expression for these two reactions. So here we have calcium oxide plus carbon dioxide gives us calcium carbonate. And in here we have, what's this guy? CH3COOH. Acetic acid and water gives us, how do we change acetic acid into an ion? What do we call it? No, acetylcholine is in the synapse of your nerves. The second page where you just wrote your notes. This is acetate. So if you have acetic acid, the ion is acetate. Plus, what's this guy called? What's it called, though? I can read the letters out. No. No. Okay. All right. Let's look at A. Kc is going to be equal to the products over the reactants of only gases and aqueous solutions. What is calcium carbonate? Solid. So we've got no products over, what's calcium oxide? Solid, so we can't use it. What's carbon dioxide? Gas. Okay? That's what the Kc constant's going to be. If I look at B, it's going to be products over reactants. What are my products? What are their states? So can I use them? Yes or no? What about in my reactants? Can I use both of those? No. What can I use? And what is the coefficient of acetic acid, acetate, and hydronium ion? 1. So they're all raised to the power of 1, which means that's the number. Okay? So we can't use calcium oxide, and we can't use calcium carbonate, and we can't use water because they're solids and liquids. Except for, exception to the rule, if they're all liquids. If they're all solids, then they're all solids. But if they're all liquids, then we can do mixtures of liquids can be included since the concentration can be varied by changing the amounts of the mixed liquids. So if I had 10 mils of bromine and 10 mils of water, and then I get whatever product, if I change it to 7 mils or 12 mils, that's going to change the interaction. So in this one, we're going to have C6H5Br and HBr over C6H6 because they're all liquid. Okay, equilibrium constants can be used to determine which side of the reaction will favor. This is only if you have the same number of reactants and product molecules in the balanced chemical equation. So if the equilibrium constant is very large, the concentration of the products is much greater than that of the reactants, right? So Kc is equal to products over reactants. In order for this constant to be large, this either has to be large or the reactants have to be small. If the equilibrium constant is very small, then the concentration of reactants is large. Whoops, small, sorry. Okay? When the equilibrium constant has a value of roughly 1, either like 1 or 0.1 or 1 or -1, the concentration of the reactants and the products are approximately equal. So let's look here. How would you get a negative value? It depends what you're working on. If you have a fraction, so like we work with 5/2 of oxygen, I don't know. I've never seen a negative K value, but I don't work at the higher levels of chemistry. My level, it's always been a positive value. Well, maybe you only need a half of an oxygen, and so now you're oxygen to the power of 1/2, which is to the power to the -2, right? Yes, no, Declan? No? Okay. Nitrogen and oxygen gives us nitrous oxide. And the Kc value is times 10 to the -25. Is the Kc value very large or very small? So if it's very small, are the reactants or the products favored?
But it's not the same. It's not the same reactants and products.
What?
It's not the same reactants and same number of reactants and products.
No, it doesn't have to be.
This is valid if the immediate reaction has the same number of reactants.
Yeah, there's 2 nitrogens, there's 2 nitrogens, there's 2 oxygens, there's 2 oxygens. Has to be balanced. Yeah. Okay, carbon dioxide and water give us carbon dioxide and hydrogen gas. Carbon monoxide and water gives us carbon dioxide and hydrogen gas. The Kc value is 5.09. Okay, well, it's going to be that value. Something to the power of -1 is going to be 1 over that value. Chances are 0.1. So is 5.09, is it to the power of 1? So this is going to be approximately equal. Okay, do we understand that last third one? It would have to be 5.09 times 10 to the power of 2. It's no longer to the power of 1 or to the power of -1. Bigger than 1. Yeah, it's now considered small. Okay?